2.2. Steady state is a balance between the energy required by the working muscles and the rate of oxygen circulating the body to get to the muscles. On graphs you'll be able to identify steady state, as the results will plateau as the muscle's demand has been met. For heart rate, I predict that the heart rate will increase quickly at the beginning of exercise, however it will then plateau. There will be an increase due to the anticipatory rise. The emotional stimuli will detect your body is about to exercise. This stimuli will then stimulate the release of adrenaline in your blood, which will increase the heart rate. At the start of exercise, it will also increase. This is because the receptors, so your chemoreceptors, proprioceptors and baroreceptors, will detect an increase in chemicals such as oxygen and carbon dioxide, an increase in movement, and an increase in blood pressure. The receptors will then send an impulse to the sympathetic nervous system, which stimulates the SA node, causing an increase in the heart rate. However, it will then plateau after a while, due to the working muscles' demand for oxygen being met with a sufficient amount of oxygen as the athlete is performing steady-state exercise. This means the chemoreceptors will no longer be detecting a demand for oxygen, so won't send an impulse to the cardiac control center, which will cause an increase in the heart rate as it will go down the sympathetic nervous system, stimulating the SA node. My quote for heart rate is, although heart rate increases rapidly with the onset of activity, providing exercise intensity remains constant, heart rate will level off. This is known as steady-state heart rate. Stroke volume. Stroke volume is the amount of blood pumped out of the heart in one beat. There will be an increase due to the increased amount of venous return. This is because the working muscles' demand for oxygen has increased due to the increase in intensity of exercise. So more blood will be returning back to the heart. The heart fills with more blood so that more is able to circulate around the body. However, stroke volume will plateau as the intensity of exercise will remain constant during steady-state exercise. The muscles will be supplied with sufficient oxygen so the heart no longer needs to keep increasing the amount of blood that gets pumped out. The average stroke volume for an adult at rest is 70 millilitres, whereas an elite athlete such as Mo Farah's stroke volume is 110 millilitres at rest. My quote for stroke volume is, stroke volume may increase only up to 40 to 60% of maximal capacity, after which it plateaus.
Cardiac output is the amount of blood pumped out of the heart in a minute. This will increase as there will be an anticipatory rise pre-exercise, which will increase both stroke volume and heart rate. This will then increase the cardiac output as the muscles will begin to demand more oxygen as the intensity of exercise increases. Once the intensity of exercise plateaus and has reached steady state, the muscles' demand for oxygen will no longer increase. Therefore, no more blood needs to be pumped out of the heart. So cardiac output will plateau. The average cardiac output for a person at rest is 4.9 litres per minute, whereas Mo Farah's is 3.63 litres per minute, which shows that an elite athlete's cardiac output will be lower, meaning their muscles around the heart are stronger. If my quote for cardiac output is, if either heart rate or stroke volume increase, or both, cardiac output increases also.
Blood flow. Once exercise starts, the receptors will detect changes in the body. The chemoreceptors will be detecting an increase in oxygen as the working muscles begin to need more. The proprioceptors will detect an increase in movement, and the baroreceptors will detect an increase in blood pressure. These increases will cause an increase of the heart rate as the muscles need more oxygen. This means they take priority, so the blood vessels will vasodilate and vasoconstrict, so that more blood flows to the muscles. My quote for blood flow is, cardiac output adapts so that more blood can be delivered where it is needed, the working muscles. Blood pressure. The force and rate of the heartbeat and the diameter and elasticity of the arterial walls. At the start of exercise, the blood pressure increases. There is a greater increase in systolic blood pressure than diastolic blood pressure. To help reduce blood pressure, blood vessels will vasodilate. However, at the start of exercise, there is an increase in cardiac output, which will increase the blood pressure. The blood pressure will plateau once steady state is reached, as the cardiac output will plateau as the demand for oxygen has been met. My quote for blood pressure is, "The increase in blood pressure caused by an increase in cardiac output." Thermoregulation. As you begin to exercise, your body temperature will increase. Due to this increase in temperature, your body will begin to sweat as it starts to try and cool the body down. There will be an increase in plasma volume in the blood, which helps to support the sweat glands when the body heats up. My quote for this is, "Trained athletes store less heat early during steady state exercise, reaching thermal steady state sooner." Venous return. There will be an increase as more blood has to flow back to the heart to then be redistributed back out to the body to the working muscles. However, when the athlete reaches steady state, there will be a constant supply of blood flow back to the heart, as the heart rate will plateau, so there won't be an increase of blood circulating around the body. Starling's law implies that stroke volume will increase in response to the heart filling with more blood, so it is therefore dependent on venous return. So at the start of exercise, the increase in venous return will also increase stroke volume, and when steady state is reached and venous return plateaus, so will stroke volume. Tidal volume is the amount of air breathed in and out in a single breath. At the start of exercise, it will increase due to an increase in the demand of oxygen from the muscles. It will then start to plateau due to the muscles being supplied with a sufficient amount of oxygen. Therefore, tidal volume does not need to increase, and it will stay at a constant level. My quote for this is, "Exercise causes an increase in tidal volume because your requirements for oxygen go up." Breathing rate. It will increase due to the emotional and volitional stimuli before the start of an event. An impulse will be sent to the DRG and then down the intercostal nerve. It then causes the external intercostal muscles and the diaphragm to contract, which increases the breathing rate. The peripheral feedback also helps control the breathing. For example, the chemoreceptors will detect changes of the chemicals in the blood, such as an increase in oxygen as the muscles demand more. Once the athlete reaches steady state, breathing rate will plateau because the muscles' demand for oxygen won't increase, as the intensity of exercise is staying constant. The chemoreceptors will detect the same level of oxygen in the blood, and the proprioceptors will detect the same amount of movement, therefore they won't send impulses to the DRG to increase the contractions of the respiratory muscles. The normal breathing rate for an adult at rest is 12 to 20 beats per minute, breaths per minute, whereas an athlete's would be lower, as their intercostal muscles and other respiratory muscles would be stronger, so they don't need to breathe as much. My quote for breathing rate is, "During steady state exercise, breathing rate will remain constant." The oxygen dissociation curve. On this graph, the red line represents the oxyhemoglobin saturation at rest, whereas the blue line is during exercise. The graph shifts to the right as there is an increase in temperature and an increase in acidity during exercise. The increase in temperature is caused by the muscles' contractions as they produce kinetic energy, which creates heat energy as a waste product. There will also be an increase in acidity during aerobic exercise, as the waste product of respiration is carbon dioxide and hydrogen, as they have a reaction in the bloodstream which causes the pH in the bloodstream to decrease. This shift to the right causes more oxygen to be released from the hemoglobin, as the oxygen in oxyhemoglobin is replaced by hydrogen into the muscle tissues, which gives us the energy we need during exercise. The aerobic energy system produces ATP. It uses 3 reactions to do so. The first is aerobic glycolysis. As oxygen is present, the pyruvic acid bonds with coenzyme A to form acetic-CoA. The second is the Krebs cycle, which uses the acetic-CoA from aerobic glycolysis, which is then combined with oxalic acid, forming citric acid. This citric acid is then oxidized as oxygen is present. The oxidation reaction forms 4 compounds: carbon dioxide, hydrogen, 2 ATP molecules, and oxalic acid. It's known as the Krebs cycle because the reaction produces oxalic acid, which means it can continue to combine with acetic-CoA to produce citric acid, so the cycle can continue. The third is the electron transport chain, which uses the hydrogen that was produced in the Krebs cycle, which binds to NAD and FAD, which are transport enzymes. This then produces NADH and FADH. The hydrogen molecule is split into ions and electrons. The hydrogen ions are oxidized and form water, which gets removed as you breathe out. The hydrogen electrons produce 34 ATP molecules. In total, this energy system produces 38 ATP molecules, and the whole energy system lasts for longer than 3 minutes. Our hypotheses: the cardiovascular response to steady state exercise. We predict that the heart rate will plateau after 3 minutes of steady state exercise. With the respiratory response to steady state exercise, we predict that the breathing rate will also plateau after 3 minutes of steady state exercise. With the energy system's response to steady state exercise, we predict that the main system used will be the aerobic energy system. There are 3 different types of hypotheses. The null hypothesis is a hypothesis where there isn't a big difference between specified populations. A two-tailed hypothesis predicts one outcome so that the results can go in 2 different directions. A single-tailed hypothesis predicts that the results will only go in one direction. The method for the experiment is to attach the heart rate monitor. We are then going to measure the heart rate, breathing rate, blood lactate levels and oxygen saturation levels of the participant before they start the exercise. To take the heart rate, we're going to use the heart rate monitor. To measure the breathing rate, we're going to observe their chest movements and count the breaths for 30 seconds, then double it. To measure the blood lactase levels, we're going to prick their finger and use the lactase monitor. And lastly, for oxygen saturation, we're going to use the saturation monitor. Our participant is going to warm up for 5 minutes on the bike. This helps to warm up the muscles that they will be using during the exercise. We're then going to attach the resistance to the bike that is acquired by weighing and measuring the person's height. We are then going to begin the exercise. Our method: at the beginning of exercise, the performer will begin the exercise. 1 minute into the exercise, we are going to take the participant's breathing rate. 2 minutes into exercise, we're going to take the heart rate and we're going to measure the lactate levels in the blood. At 3 minutes, we're going to measure the breathing rate. 4 minutes, we're going to measure the heart rate. At 5 minutes, we're going to measure the breathing rate, the blood lactate levels, and the RPE. At 6 minutes, we're going to take the heart rate. At 7 minutes, breathing rate is going to be taken. At 8 minutes, heart rate is going to be taken. At 9 minutes, breathing rate is going to be taken. At 10 minutes, heart rate and blood lactate is taken. At 11 minutes, breathing rate is taken. At 12 minutes, heart rate is taken. At 13 minutes, breathing rate is taken. At 14 minutes, heart rate is taken. At 15 minutes, breathing rate is taken and lactate levels are taken. 16 minutes, the heart rate is taken. 17 minutes, breathing rate is taken. 18 minutes, heart rate is taken. 19 minutes, breathing rate is taken. At 20 minutes, heart rate is taken and blood lactate levels are taken.